second online class of the force and pressure part, and happy Independence Day to you. So in this chapter we are going to discuss the pressure part. Okay, so up to liquid pressure or manometer we can say. So I have already discussed it in our online classes, but now here I am adding some videos so that you can understand it clearly. Okay, let's start. When you hammer an iron nail, you apply force on the flat side of the nail, the pointed side of the nail, which is in contact with the wall. Then applies the force on the wall and tries to pierce it in. Now, let me ask you an interesting question. What will happen if you hammer the pointed side and try to pierce the flat side of the nail? You will find it difficult to push the flat face of the nail through the wall, even if you apply more force than you did in the first case. What is the reason for this? The reason is that the pressure applied by the tip of the nail on the wall is more than the pressure applied by the nail's flat surface. But the question is why? First, notice that the area of the tip of the nail is very less as compared to the area of its flat surface. This tells us that the area of the surface on which the force is applied matters. We'll understand this in detail, but let us first define pressure. So, we define pressure as the perpendicular force acting on the surface of an object per unit area on which it is acting. It's easy. Force acting per unit area. We already know that the SI unit of force is Newton, and it is denoted by N, and that of area is meter squared. So it is called Pascal, which is denoted by PA. Why is it Pascal? It is given this name to honor the achievements of a French scientist named Blaise Pascal. Clear? Now, observe the equation carefully. Area is in the denominator of the fraction. What is this area? Well, this area is nothing but the area on which force is applied. Say I keep the force constant and I keep increasing this area. What will happen to the pressure? Will the pressure increase or decrease? By using pure mathematical logic, we can say if I have a fraction and I keep the term in numerator constant and keep increasing the term in the denominator, then will the fraction increase or decrease? Surely it will decrease, right? So the pressure will decrease if I increase the area while keeping the force constant. With this newfound knowledge, let's go back to the example we saw earlier, the nail and the wall. Notice that we are also applying force perpendicular to the surface of the wall. The angle between the nail and the wall is 90 degrees and nothing else. If you notice, the tip of the nail has a very small area compared to the flat surface of the nail, and hence the area of contact with the wall reduces to a great extent in the first case. Hence the pressure applied by the tip of the wall is greater than the pressure applied by the flat surface. That is why it is easier for the tip of the nail to penetrate through the wall. You can even use drill machines to drill the hole into the wall. Okay, you see that it has a pointed tip. For the same reason, you can easily cut the vegetables using the cutting edge of the knife, but if you use a blunt edge of the knife, it will be very difficult to penetrate it in. What is the reason in this case? Well, in the first sight, the two edges might look the same to us, but if we look them carefully, the cutting edge has small triangle like shapes which has sharp outer points. The other edge has nothing of this. So if you cut vegetables with cutting edge, the area of contact between the vegetables and the knife is greatly reduced. Hence, more pressure is applied on the vegetables using cutting edge of the knife. Axes used to cut trees also have sharp cutting edges instead of placid ones. It increases the pressure on the tree due to the less area of contact. The examples that we have seen so far are applications of high pressure. It's about how high pressure is useful to us in some cases, but it is not always the same case. There are situations where we require low pressure. So let us see some applications or advantages of low pressure. We use snow shoes to walk on snow. The reason for that is simple. Due to the larger area in contact with the snow, snowshoes reduces the pressure on the snow. We are able to walk on it without feet sinking deep inside. In case of normal shoes, due to comparatively small area of contact, the pressure on snow is more and it sinks out feet deep inside. Note that the force applied on the snow in both the cases is the same. This force is nothing but our weight on the snow. Have you ever wondered why the wheels of an army tank run on steel tracks rather on the ground? Notice that the wheels are on steel tracks are not touching the ground. The army tank is huge in size. If the wheels run on the ground due to less contact area with the ground, the pressure on the ground will be massive. However, the tracks have much larger area of the contact with the ground, and hence the pressure on the ground is reduced to a great extent. So these are the examples of solid, pressurized solid. But what about liquids? Okay, let's see the if liquids exert pressure or not. Pressure in liquids. A wooden block kept on a table exerts a force on it, and we know that the wooden block is a solid substance. What about liquids? We know that the liquids are kept in containers. Do liquids or fluids exert pressure? Yes, they do. They exert pressure on the base and the walls of the container in which they are enclosed. The pressure on the base will be downwards, and on the walls, the pressure will be sidewards. We can also derive something interesting if you look at the fluid in terms of layers. Say there's a water kept in a plastic container. Let's divide the fluid into 5 equal parts. You can see that the second layer of the water is holding the weight of the first layer. Similarly, the third layer is holding the weight of the first as well as the second layer. And the fourth layer is holding the weight of the top 3 layers, and so on and so forth. So clearly the pressure at the bottommost layer is the maximum. There's even a way you can find out this. Near the topmost layer, make a little hole at the side. You will see that the water flows out from that hole like this. It does not roll along the walls. It flows out at an angle. Now let's make a second hole near the layer under it. You will see that the water flows out at a wider angle as compared to the earlier case. We continue to make holes in the walls and we notice that the water literally squirts out. This proves that the pressure at the bottom is much more than the pressure at the topmost layer. So that's how the liquid is exerting a pressure. Okay, now moving on to the next topic, which is the manometer, which is to measure the liquid pressure. Liquid pressure, measuring the liquid pressure. An instrument called a manometer is used to measure liquid pressure, which we already know. So it contains a glass U-tube fixed to a stand with a scale. It is half filled with water, or you can fill it with mercury. One end of the U-tube is open, the other end is attached to a thistle funnel through a flexible tube. The mouth of the thistle funnel is covered with a tight, thin rubber skin. When the thistle funnel is kept in the air, only atmospheric pressure acts on it. This is equal to the pressure acting on the open end of the U-tube. Therefore, the water levels in the two sides of the U-tube remain the same. Dip the thistle funnel in a bucket of water. Now the liquid pressure acts on the rubber skin. As the liquid pressure on it increases, the water level in A will go down and in B will go up. The difference in water levels can be read on the scale. This is a measure of the pressure exerted on the rubber skin. So this is the working of the manometer. Okay, this much is for today, and in the next video I'll try to explain the atmospheric pressure along with the barometer and along with some everyday day-to-day examples of atmospheric pressure. Okay, so see you in the next video. Okay, thank you.